Hi Bob, I've been reviewing the quantum computing papers from May 2025, and there's quite an impressive range of work. I'm curious about your thoughts on the key developments. It seems like we're seeing advances across multiple fronts, from theoretical frameworks to practical implementations.
Absolutely, Alice. May 2025 was particularly rich. I'm especially struck by the breadth. From foundational work on paraparticle algebras to concrete demonstrations of quantum advantage. The paper by Tamburini et al. On graded paraparticle algebra of Majorana fields for multidimensional quantum computing with structured light really caught my attention. They're extending quantum computing beyond traditional fermions and bosons, using Z2 times Z2 graded algebras.
That's fascinating. I found that paper quite challenging to digest. Can you explain how their approach with structured light and Majorana quasiparticles could enable deterministic two-photon gates without nonlinear effects? That seems like it could be a game-changer for photonic quantum computing.
Great question. The key insight is that they're using the graded algebraic structure to encode multiple qubits in a single photon through spin and orbital angular momentum. By mapping spin-dependent mass spectra to graded sectors with generalized quantum statistics, they can implement gates that would normally require nonlinear interactions. This makes photonic platforms much more viable for universal quantum computing, since nonlinearity is typically the bottleneck.
That's remarkable. Speaking of practical implementations, I was impressed by the low-overhead quantum error correction demonstration by Wang et al. They implemented QLDPC codes on a 32-qubit superconducting processor with logical error rates around 8 to 9%. How significant is this compared to previous error correction demonstrations?
This is huge, Alice. Traditional error correction codes like surface codes have very high overhead. You need hundreds or thousands of physical qubits per logical qubit. Wang et al. Demonstrated distance 4 bivariate bicycle codes and distance 3 QLDPC codes with much better encoding efficiency. The fact that they achieve this on actual hardware with long-range couplers shows we're moving toward practical, fault-tolerant quantum computing much faster than expected.
The efficiency gains are impressive. I also noticed Gidney's updated analysis of factoring 2048-bit RSA with less than 1 million noisy qubits. How does this compare to the 2019 estimate of 20 million qubits, and what are the main technical improvements driving this reduction?
Gidney's new estimate is a dramatic 20 times reduction in qubit requirements. The main improvements come from 3 sources: approximate residue arithmetic from Chevignard et al., yoked surface codes for storing idle logical qubits, and magic state cultivation instead of traditional distillation. The trade-off is longer runtime, about a week instead of 8 hours, but the qubit reduction makes this much more feasible for near-term quantum computers.
That timeline shift is quite significant for cryptographic planning. Moving to applications, I was intrigued by the quantum machine learning developments. The paper on quantum knowledge distillation for large language models by Li et al. Seems to address the massive resource requirements of LLMs. What's your take on their QD-LLM approach?
The QD-LLM approach is clever. They're using quantum student models to mimic LLM behavior, with only 0.072% of the parameters. The key insight is leveraging quantum superposition and entanglement to capture complex patterns that would require massive classical networks. While we're still early in quantum machine learning, this kind of compression could be transformative if quantum hardware scales appropriately.
The compression ratios are remarkable. I also noticed several papers on quantum algorithms for specific domains. The work by Schmidbauer et al. On Monte Carlo option pricing in quantum parallel, and the paper by Jin et al. On quantum circuits for Black-Scholes equations, both target financial applications. Are we seeing quantum computing mature enough for practical financial modeling?
These financial applications are particularly promising because they naturally involve high-dimensional probability distributions and complex Monte Carlo simulations, exactly where quantum computers could excel. Schmidbauer's approach uses quantum superposition to simulate exponentially many asset paths in parallel, while Jin's Schrödingerization technique converts the Black-Scholes PDE into a unitary evolution problem. Both could offer genuine quantum advantages for derivative pricing and risk analysis.
The financial sector applications seem very concrete. What about the optimization landscape? I saw several papers addressing QUBO problems and quantum optimization. How do you assess the current state of quantum optimization algorithms, particularly the comparison between QAOA and newer approaches like VQPM?
Quantum optimization is really heating up. Daskin's analysis of VQPM shows it can be quite effective for QUBO problems, potentially offering advantages over QAOA in certain scenarios. But the real excitement is in Majorana et al.'s experimental demonstration of runtime quantum advantage with their BF-DCQO algorithm on IBM's 156-qubit devices, actually outperforming simulated annealing and CPLEX for specific problems.
That runtime quantum advantage claim is significant. Speaking of practical implementations, I noticed several papers addressing the engineering challenges of quantum computing. The work on hybrid quantum classical systems seems particularly important. What are your thoughts on the integration challenges discussed in papers like the QMIO system and the quantum classical optimization work?
The hybrid approach is absolutely critical for near-term quantum computing. The QMIO system by Kashiro et al. Represents a significant step toward tightly integrated HPC-QC systems, while Remy et al.'s work on optimizing hybrid quantum classical algorithms addresses a previously neglected area. We need sophisticated optimization at the hybrid level to make these systems practical, not just optimize the quantum circuits in isolation.
The systems integration aspect is crucial. I'm also curious about the networking and communication side. The papers on networked quantum services and quantum transduction seem to address the challenge of building distributed quantum systems. How realistic are these quantum networking visions?
Quantum networking is advancing rapidly. Gyongyosi and Imre provide a comprehensive overview of networked quantum services, while Kalefi et al.'s work on quantum transduction addresses the critical challenge of interfacing different quantum platforms. Shabani's satellite constellation proposal for a global quantum internet is particularly ambitious. Using LEO satellites with intersatellite links could achieve megahertz entanglement distribution rates between continents.
The satellite approach is fascinating for global scale. What about the security implications? I noticed several papers on post-quantum cryptography and quantum security protocols. With quantum computers potentially breaking current cryptography, how are the quantum-safe solutions developing?
The post-quantum cryptography landscape is evolving quickly. Riva Cambrin et al.'s work on extensible PQC authentication shows how lattice-based algorithms can be integrated into practical systems. The energy consumption analysis by Patterson et al. Is particularly important for embedded devices. And the onion routing relay approach by Otero Garcia et al. Adds an interesting privacy layer to quantum key distribution networks.
Security and privacy are definitely critical. I'm also interested in the quantum simulation applications. The papers on molecular dynamics, protein quantum properties, and chemical simulations suggest quantum computing is making inroads into computational chemistry and biology. How mature are these applications?
Quantum simulation for chemistry is one of the most promising near-term applications. Bickley et al.'s work on extending quantum computing through subspace and embedding techniques shows how to make quantum algorithms practical for real chemical systems. The QM-Prot dataset by Koronis Sala and Achide Adalomu provides crucial quantum mechanical data for proteins, while Verma et al.'s review of multi-reference embedding methods bridges classical and quantum approaches beautifully.
The chemistry applications seem very promising. What about the more fundamental algorithmic developments? I saw papers on quantum algorithms for PDEs, Hamiltonian simulation, and various mathematical problems. Are we seeing new classes of quantum algorithms emerge?
Absolutely. Devereaux and Data's 3 quantum algorithms for drift diffusion equations show quantum advantages for PDEs, while Lubosch et al.'s QFT-based circuits for PDEs in Fourier space are remarkably elegant. The hadron scattering simulation by Davudi et al. Demonstrates quantum computers can handle complex gauge theory problems. We're definitely seeing quantum algorithms mature beyond the early proof-of-concept stage.
The algorithmic diversity is impressive. I'm also curious about the hardware and architecture developments. Papers on neutral atom computing, superconducting circuit improvements, and quantum control systems suggest significant hardware progress. What are the key hardware trends you're seeing?
Hardware is advancing on multiple fronts. Stade et al.'s routing-aware placement for neutral atom systems shows 17% average improvement in rearrangement time. The superconducting circuit shielding guide by Malavagna et al. Addresses practical decoherence challenges, and Liu et al.'s RISC-Q framework for quantum control systems brings much-needed standardization to quantum hardware control, making it compatible with RISC-V ecosystems.
Hardware standardization efforts are encouraging. I also noticed some interesting work on quantum algorithm design automation. The papers on differentiable quantum architecture search and automated circuit design seem to address the challenge of making quantum computing more accessible to non-experts.
That's a crucial development area. Chen et al.'s differentiable quantum architecture search automates the design of quantum neural networks, while the Canadian Innovations Review by Saxena et al. Highlights the importance of making quantum error correction more systematic. We need these kinds of automated tools to democratize quantum computing and move beyond requiring deep quantum expertise for every application.
Automation and accessibility are definitely key for widespread adoption. Looking at the educational side, I saw the paper on introducing quantum computing to high school curricula. This seems important for building the next generation of quantum-literate researchers and engineers.
Education is absolutely critical. Versailles et al.'s work on high school quantum curricula addresses a real need. We're seeing quantum computing move from a highly specialized field to something that needs broader understanding. The modular integration strategy they propose could help build quantum literacy without requiring complete curriculum overhauls.
That's a good point about building quantum literacy. What about some of the more specialized applications? I noticed papers on quantum computing for music composition, anomaly detection, and even software engineering. Are these niche applications, or do they represent broader trends?
These applications show quantum computing's versatility. Dobrian and Hamido's work on quantum-aided music composition explores quantum simulation for creative decision-making. Quite novel. Hamami et al.'s quantum GANs for network anomaly detection demonstrates practical security applications, and Zhao's quantum-based software engineering framework suggests quantum optimization could revolutionize how we approach classical software problems.
The creative and software engineering applications are fascinating. I hadn't expected quantum computing to branch into those areas. Looking across all these papers, what do you see as the major themes or trends emerging in May 2025's quantum computing research?
I see several major themes. First, the transition from proof of concept to practical utility. We're seeing real quantum advantages demonstrated on actual hardware. Second, the integration challenge. Hybrid systems, networking, and standardization are becoming critical. Third, the expansion into diverse application domains beyond the traditional quantum algorithm targets. And fourth, the democratization effort, making quantum computing accessible through automation, education, and better tooling.
Those themes really capture the maturation of the field. It seems like May 2025 represents a pivotal moment where quantum computing is transitioning from a research curiosity to a practical technology with real-world applications. The combination of hardware advances, algorithmic improvements, and systems integration work suggests we're entering a new phase of quantum computing development.
Exactly. What's particularly exciting is how these advances are reinforcing each other. Better error correction enables more complex algorithms, improved hardware makes practical applications feasible, and automated tools accelerate the entire development cycle. May 2025 might be remembered as the month when quantum computing truly began its transition to practical utility across multiple domains.
That's a great way to put it. Thank you for this insightful discussion, Bob. It's clear that the quantum computing landscape is evolving rapidly, and these May 2025 papers provide a fascinating snapshot of a field in transition. The breadth of applications and the depth of technical advances suggest we're on the cusp of some truly transformative developments in quantum computing.